Welcome again in my online session on modern spectroscopic techniques of analysis. This time we'll talk about calculation or theoretical calculation of lambda max by Woodward Fieser Rule. Till now we have talked about lambda max, that we discussed it is a wavelength where it shows maximum absorbance. Experimentally, this lambda max can be found by preparing various standard solutions and scanning in a given range and identify a wavelength where it shows highest absorbance. That will be its lambda max practically. But theoretically also, it is possible to calculate lambda max on the basis of Woodward Fieser Rule. For that purpose, the structure of a compound is required and different categories are prepared. On the basis of that categories, the parent values and increments for a typical oxychromes, this data is available. So we can follow this data and we can calculate theoretically lambda max value for a particular compound. Now here we can consider the first class for calculation of lambda max, that is dienes. What is diene? Means two double bonds in conjugation. If you look at this structure, this is the general structure of diene, where you can see a double bond, single bond, double bond. It's an alternate double bond. So it is a diene system. So if in a given structure you have such a kind of diene system, then let us see how to calculate lambda max for this kind of compounds. For that, there are some parent values given. If it is acyclic and heteroannular conjugated diene, the parent value for this is 215 nanometers. Now what is acyclic? Acyclic means a non-cyclic or straight chain compound, or heteroannular conjugated diene. When we are talking about diene, means there are two double bonds in conjugation. If it is a heteroannular diene, means two conjugated double bonds, if they are in different ring, it is called as heteroannular conjugated diene. If system is like this, then you can take parent value as 215 nanometers. Secondly, homoannular conjugated diene. In this, two double bonds which are in conjugation, both are in a same ring system. In that case, you have to take 253 nanometers as a parent value. Then acyclic triene. Triene means three double bonds in conjugation, and it's a acyclic system, means it's a non-cyclic or straight chain system. In that case, the parent value given is 245 nanometers. In addition to this, we have to add if certain following conditions exist in the structure, like double bond extending conjugation. Here, if there is additional double bond present along with a diene system, when we are saying diene, this is a diene, two double bonds in conjugation. In addition to these two, if at all there is any additional double bond, and if that additional double bond is in conjugation with this diene system, then it needs to add 30 nanometers in the parent value. Then exocyclic double bond. Here exocyclic double bond means a double bond shared between two carbons. Out of that, one carbon is a part of ring and second carbon is not part of same ring. If this is a structure where a double bond in which one carbon is a part of one ring system, but another carbon sharing a same double bond is not part of same ring system, in that case it needs to add 5 nanometers in the parent value. Then if there is a substitution on allylic carbons, here in a diene system we have to identify allylic carbon. allylic carbon is a carbon sharing double bond. Here, if you look at this, these two carbons are sharing this double bond. So, these two are allylic carbons. Again, this double bond is shared by again these two carbons. So, again, these two are allylic carbons. So, total in this structure, there are total 4 allylic carbons. So, we have to check substitution on such a allylic carbons. On allylic carbon, if there is alkyl group or a ring residue, in subsequent slides we will see what is ring residue and all. So, if at all there is any alkyl group or ring residue on allylic carbon, we have to add 5 for each such a substituent, each such alkyl substituent or a ring residue. If there is any oxochrome present on this allylic carbon, like OR for that 6 nanometers, SR 30 nanometers, chlorine or bromine 5 nanometers, NR2 60 nanometers, or if there is any S-toxy group OCOCH3, in that case there is no need of addition of anything. So this is what is a parent structure proposed by Woodward to calculate a lambda max value for a given structure. So let us see how this given data of Woodward Fieser rule, how it could be applicable for calculation of lambda max. Now look at the structure. If we try to apply this Woodward Fieser rule for calculation of lambda max in this case, then once we look at the structure, we have to see that whether what kind of structure it is, what kind of class it contains. So here we can see that there are 2 double bonds in conjugation. So it is a diene system. Up till now we have seen only dienes. So okay, it's a diene. Double bond, single bond, double bond. So these 2 double bonds are in conjugation, alternate double bond. Again, this ring system has only one cyclic structure, and one double bond is in the cyclic structure, another double bond is out of the ring. So it is not a homoannular diene, it is a kind of heteroannular diene. Now another part we have to see whether it has any double bond extending conjugation. For having a double bond extending conjugation, there should be one more double bond in addition to the diene system. If you look at this, here is a diene, but there is no any additional double bond along with this diene system. So there is no question of double bond extending conjugation. Then we have to check for any exocyclic double bond. As I told, the exocyclic double bond is one whose one carbon is a part of ring, another carbon is not part of same ring. Here, this double bond is shared between these 2 carbons, both are part of ring. The second double bond is shared between these 2 carbons, again both carbons are out of ring, so there is no exocyclic double bond. Then we have to check for substitution on allylic carbon. Here first identify allylic carbons. This is first allylic carbon, second, third and fourth. On first allylic carbon, the part of ring is connected. So there is one ring residue on this first allylic carbon. Again on the second allylic carbon, part of ring is connected. So another ring residue is on second carbon. Third and fourth allylic carbon, there is no substitution. So in all, in this particular compound, the parent value is for heteroannular diene and 2 ring residues at allylic carbon. No exocyclic double bond, no double bond extending conjugation, no any other substitution. So summation of these 2 things will be a lambda max value in nanometers for this particular compound. Okay, now if we look at the second, here again it is a diene system, double bond, single bond, double bond. So alternate double bond it is in conjugation. This compound is having two rings, say ring A, ring B, and these two double bonds are in different rings. The first double bond is in ring A, second one is in ring B, so it is a heteroannular diene. No question of homoannular diene. Then similarly, there are only two double bonds in this structure, so no question of double bond extending conjugation. We have to check for exocyclic double bond. For that, this first double bond is formed by these two carbons, carbon 1 and carbon 2. This carbon is part of ring B, but this carbon is not a part of ring B, so first double bond is exocyclic to ring B. In this case, the first carbon of the double bond is part of ring A, while a second carbon of this double bond is not a part of ring A, so the second double bond is exocyclic to ring A. Thus, this structure have two exocyclic double bonds. Then identify allelic carbons. This 1, 2, 3 and 4. The first allelic carbon, there is one ring residue and one alkyl group. On second, ring residue. Third, again one ring residue. And fourth, again ring residue. So there are total 4 ring residues and 1 alkyl substitution. So like summation of all this, heteroannular diene as a parent value, 2 exocyclic double bonds, 4 ring residues and 1 alkyl group. The total of this is a lambda max value for this compound. Now look at this one. Here double bond, single bond, double bond, single bond, double bond. So it is a diene system. These two double bonds are in the same ring, so it is a homoannular diene. And if we consider the different double bonds, then it may be heteroannular, but the value for homoannular diene is higher than heteroannular, so we have to consider a homoannular diene as a parent value. So this is a homoannular diene. In this, there is one more double bond is in conjugation with homoannular diene. So there is one double bond extending conjugation. Then check for exocyclic double bond. This 2 carbons in a same ring, no exocyclic. 2 carbons in a same ring, no exocyclic. 2 carbons in a same ring, again no exocyclic. So there is no any exocyclic double bond. Homoannular diene, 1 double bond extending conjugation and substitutions. For this allelic carbon, 1 ring residue, 1 alkyl group. Here no substitution. Here 1 ring residue. On this carbon, 1 more ring residue. On this carbon, 1 OCOCH3, but we don't have to add anything for this substitution because it has 0 addition. And on this carbon, there is 1 more ring residue. Like this forms a lambda max value of this particular compound. Now this is something different. If you look at the structure, there are 3 double bonds. They looks like they are alternate, but this double bond is not in conjugation with this diene system, or this double bond is not in conjugation with this diene system. This is a heteroannular diene system, whereas this one is a homoannular diene system. In this particular structure, both system exist, homoannular as well as heteroannular, but we have to consider a homoannular system because it has a higher value. So being a homoannular system and this double bond is not in conjugation, so it's a homoannular diene, no double bond extending conjugation. Here, for exocyclic double bond, both carbons in one ring, both carbons in one ring, so no question of exocyclic double bond. And so, look for substitution on allylic carbon. Here, one ring residue. Here, no substitution. Here, this is an alkyl group. So, we can consider alkyl substitution at this carbon. And on this carbon, one more ring residue. So, likewise, two ring residues and one alkyl substitution. Homoannular diene. This is how it forms the lambda max value for this particular compound. Now, let's move to next. Actually, you can have exercise on this. These are the different structures. You can find its lambda max value using the table of the data given for Woodward Fieser rule, and we may discuss in the open session. Likewise, again, the few examples are, a few structures are given here, so need not to explain the similar things. You can try this and we may have a discussion on this. Now, another category, we will move on to the another category which is proposed by Woodward for calculation of lambda max, and it's a enone. What is an enone? Is alpha, beta, unsaturated aldehyde or ketone. If you look at this functional group, in this functional group, C double bond O H. If here it's H, it is CHO aldehyde. If C double bond O R, if here there is any alkyl group, then it becomes a ketone. So from this carbonyl carbon of either aldehyde or ketone, from this carbonyl carbon, if we count, the first one is alpha carbon, second one is a beta carbon. So if there is alpha, beta unsaturation in aldehyde or ketone, we can call it as enone. So if such a system exists, then how to calculate a lambda max for this kind of compounds? Let us see. So see how to have apparent values for this. If it is alpha, beta, unsaturated, acyclic or 6-membered ring ketone, alpha, beta, unsaturated, acyclic, non-cyclic or 6-membered ring ketone, the value is 215 nanometers. If it is alpha, beta, unsaturated, 5-membered ring ketone, if ring is 5-membered and the same system exists, then the value is 202 nanometers. If it is alpha, beta, unsaturated aldehyde, here if there is H, and if it is aldehyde, it may be 5-membered, 6-membered, acyclic, whatever it may be, you have to take apparent value as 207 nanometers. Now, like this, we can identify a parent, whether it is aldehyde or ketone, what kind of enone it is. Then we have to give some increments in that. Increments like homoannular conjugated diene. In addition to this alpha, beta, unsaturated aldehyde or ketone, if there is any additional double bond and this additional double bond is in conjugation with alpha, beta unsaturation, then and if these two double bonds are in the same ring, so like previous dienes, if any homoannular diene system exists, in such a case we have to add 39 nanometers. Again, double bond extending conjugation. So this is a enone system. In addition to enone, if there is any double bond which is in conjugation with this enone system, then add 30. Exocyclic double bond, as discussed earlier, we have to add 5, but here we cannot consider a double bond of carbon oxygen. The carbonyl double bond should not be considered here, only carbon carbon double bond needs to be considered. Then we have to identify substitutions on various positions. In this structure, if there is alkyl group or ring residue at alpha position, so first we have to designate alpha, beta, gamma and higher positions like this. This is alpha, beta if additional carbon, gamma if higher, or delta, and likewise. So first identify or designate alpha, beta, gamma like this, and then check what are the substituents on these various carbons. At alpha, if there is alkyl group or ring residue, add 10. At beta, alkyl group or ring residue, 12. Alkyl group or ring residue, if it is there at gamma or higher positions, add 18. So these are the values. Similarly, for different oxochromes, OH, OR, SR, OCOCH3, chlorine, bromine and NR2. So for this, the values if at alpha carbon, if at beta carbon and if at gamma carbon. According to their substitution, these additions can be done in the basic values, and the summation of all this, it will come out to be a lambda max value for this particular compound. So let's look at this. This C double bond O, this is a CH3, and from this carbonyl carbon, it is alpha, this is a beta. So it is alpha beta unsaturated aldehyde, alpha beta unsaturated ketone. So here it's an enone system, and the corresponding parent value needs to be taken for this enone system. Then there is no any additional double bond, so no question of homoannular diene or double bond extending conjugation. Now exocyclic double bond, again there is one carbon-carbon double bond, and both these carbons of this double bond are a part of same ring, so no exocyclic double bond. Then substitutions for that, this is alpha carbon, beta carbon. At alpha carbon there is one ring residue, at beta carbon one more ring residue. So accordingly the addition of all these values will come to the lambda max value. Similarly here, the same kind of structure, there is only one additional double bond we can see, but it makes a lot of difference because of this one more double bond, it forms a homoannular diene. So this value needs to be added for homoannular diene. Again there is double bond extending conjugation, one more double bond is there which is in conjugation with the enone system. So double bond extending conjugation, but no exocyclic double bond. Now look for substitutions: alpha ring residue, beta nothing, gamma nothing, and higher one ring residue. So alpha one ring residue and gamma and higher one ring residue. So addition of this. If you look at this, again a enone system, it is a ketone again, alpha beta unsaturated ketone. At alpha and beta, if you look at this double bond is exocyclic to central ring A, B and C. So this double bond is exocyclic to this ring, so there is one exocyclic double bond, but there is no any homoannular diene or double bond extending conjugation. Accordingly summation of this. Here again a enone system, it's a ketone, alpha beta unsaturation, enone, these two double bonds in same ring, homoannular diene. Likewise we can go for calculation. Similarly few structures are quoted again for this particular system, enone system. So we can practice on this to find out lambda max for this class of compounds. Here it's a 5-membered ring, so we have to use a 5-membered ring system. One more thing, let me tell you about this structure, that here if we try to look for exocyclic double bonds, then 1, 2, these are 2 carbon-carbon double bonds. Here this double bond is exocyclic to ring B, this double bond is exocyclic to ring A as well as ring C. Likewise, here there are total 3 exocyclic double bonds. You can try and we'll see. Then next category for calculation of lambda max, that is alpha beta unsaturated acid or esters. See, this is a functional group, C double bond OX. If X is OH, it is COOH, that is a carboxylic acid. If X is OR, it's a COOR, that is ester. So if this acid or ester is there, and from this carbonyl carbon, alpha and beta, if there is unsaturation in alpha and beta carbons, then we can categorize this kind of compounds as alpha, beta, unsaturated acids or esters. Now, if it is a mono-substituted, if you look at this, see, tri-substitution is possible in this alpha, beta, unsaturated acid and ester. On alpha carbon, to satisfy valency of carbon, one substituent is possible. At beta carbon, to satisfy valency of carbon, again, maximum 2 substituents are possible. So alpha, beta, beta, tri-substitution, that is the highest substitution possible in this class of compounds. So if it is a mono-substituted means either substitution at alpha or beta, the value is 208. If it is di-substituted, it means if it is alpha beta or beta beta, 217 nanometers. Tri-substituted alpha beta beta, 225 nanometers. In addition to this, if there is any double bond extending conjugation like earlier discussions, add 30. If exocyclic double bond, add 5. And if at all there is 5 and 7-member ring system, add 5. This is how the lambda max could be calculated. Let's see the application of this. See, this is C double bond O. This X is OH, so it is carboxylic acid. So it is a 7-membered ring system. In carboxylic acid, from this carbonyl carbon, this one is alpha carbon, it's a beta carbon. So it is alpha is substituted by ring residue, beta is substituted by again ring residue. So it is alpha beta di-substituted carboxylic acid. Okay, so the parent value is for this is here. If you look at this, it is a C double bond O OR. So this is a ester, and from this carbon, this one is alpha, this one is beta. Alpha is substituted with 1 ring residue, beta is substituted with 1 ring residue as well as alkyl group. So it is alpha, beta, beta tri-substituted. Addition to this, there is 1 double bond extending conjugation. Again, if you look at this double bond, it is exocyclic to ring A. So there is 1 exocyclic double bond. This is how the calculations could be done for this. Then last category for calculation of lambda max theoretically is for aromatic compounds. Aromatic compounds, we need to identify whether the given compound is aromatic or not by Haeckel's rule, and if it is found aromatic, then we can apply this formula. Look, this is an aromatic one where C double bond OX. If X is H, it is aromatic aldehyde. If it is aromatic aldehyde, take 250 nanometers. If this X is alkyl group or ring residue, it is aromatic ketone, For that, it's 246 nanometers. And if this X is OH or OR, that is aromatic acid or aromatic ester, the value should be 230 nanometers. So this is a parent value for aromatic compounds. And to check substitutions on the aromatic compounds, we have to identify ortho, meta and para positions for the second substituent, right? So here this functional group is connected to this carbon of aromatic system. So this carbon should start with number 1. From this 2, 3, 4, 5 and 6. So this is a 6-membered aromatic system. From here a second and 6th, these two are ortho positions. 3rd and 5th, these two are meta positions. And 4th one is para position. Now what we have to check, if at all there are these substituents like alkyl group or ring residue or OH or 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 chlorine or bromine or amino. And if these substitutions, whether they are at ortho, meta or para positions. And accordingly the values are quoted in this table. So we can add these values according to substituent and it will come to the lambda max value of given compound. Look here, yes, it is aromatic one. Now C double bond O, this X is alkyl group, so it is a ketone, aromatic ketone. From this start numbering, number 1, 2, 3, 4, 5 and 6. So 2nd and 6th ortho, 3rd and 5th meta and 4th para. So here there is only one substituent, that is methyl group at ortho position. So add accordingly. Same thing here, but these two are ortho, these two are meta, para. There is substitution at meta position, OCH3 and chlorine. Look, this one, now this is aromatic system. Although this structure has 2 cyclic rings, but this is aromatic one. So we have to consider this is an aromatic system. From this one, C double bond O, X. So this is a functional group connected to aromatic system at this carbon. So it is C double bond O ring residue. So it is aromatic ketone. And here, from here, if you count on ortho, meta and para positions, this is ortho where alkyl group is there. This is again ortho, ring residue, meta, no substitution, para, bromo. So this is how we can go for a calculation of lambda max on the basis of Woodward Fieser Rule. Again, few examples you can try and we'll see in the discussions. Thank you.